So that brings me to the final topic, which I will review with you guys for the evening, which is going to be complex roots for second order differential equations. And again, this lecture is going to show you to what extent I expect you to understand these. So from your notes, you had this problem, y double prime minus 4y prime plus 9y equals 0. And we had the initial conditions that said y of 0 is equal to 0. And the other initial condition which said y prime of 0 is set equal to negative 8. Okay? So again, we find the characteristic equation like before. So it's going to be r squared minus 4r plus 9 is set equal to 0. All right, and when you solve for these roots, you get complex solutions. And r1 is going to be 2 plus the square root of 5 times I. And r2 is going to equal to minus the square root of 5 times I. Okay? And so when you create a solution for this, it's really not too bad at all. You guys will come up with this in just a blink of an eye once you know how this is done. This is going to equal C1 e to the 2t, this is the real part of the solution, times cosine square root 5 times t, okay, plus C2 e to the 2t, all right, times sine of the square root of 5 times t. Not too bad. So you know where the square root of 5 comes from. That's the imaginary part. And the power, which is 2, comes from the real part. Again, that's not hard at all. So with this in mind, we can easily observe something very, very clever, which is y equals y of 0, right? In this first initial condition. Well, if you plug it into the equation above, this just pops out that C1 is equal to 0. So that's a very nice little observation to point out. Just a little bit of forward thinking, you can expect something like that to appear on your final exam. And ultimately, what we can do now that we have that initial condition is we can simplify the expression y of t a little bit. So it's going to be C2 e to the 2t times sine the square root of 5 times t. Okay, so we just took advantage of the fact that C1 is equal to 0 and simplified the original equation that we had. And now, since this is a second order differential equation, we have to take the first derivative, right? And so that's going to give us 2c2 e to the 2t sine, and this is going to be the square root of 5 times t, right? And then using the product rule, we do it the other way around. This will give us the square root of 5 times c2 e to the 2t times cosine of the square root of 5 times t. Okay, it's a t. And with that being said, we can then use our second initial condition, which says negative 8 equals y prime of 0. And plugging in 0 everywhere will produce this result, which says square root of 5 times c2. So this just implies that c2 equals negative 8 over the square root of 5. Nice and easy. So therefore, since c1 is 0 but c2 is non-zero, we can say the final solution is negative 8 divided by the square root of 5 e to the 2t times sine of the square root of 5 times t. And this is the extent in which I would expect you to understand complex roots with second order differential equations. And that's it. So this is the last lecture for the review. For the other two items, please review the lectures from last week on Thursday and from today's lecture as well. Last Thursday I covered how to solve systems of differential equations with real eigenvalues. And today I showed you how to solve systems of differential equations with complex eigenvalues, and I showed you a very typical example of how to solve systems of differential equations with Laplace transforms. So you have everything you need for the finals review. I believe that perhaps on Thursday I will give you guys a taste of what the problems will look like. I'm debating that. If not, expect the test to be given on Saturday as planned. And of course, what I'd highly recommend for all of you as you start the process of review and also as you work through your homework problems for this week, please feel free to reach out if you have any questions or come to office hours. I'd be more than happy to help. All right, that's it for today. You all have a great night. Talk to you soon.